our second Webex conference. Well, what we are going to talk today is from chapter 3, basically more on the charge carriers. So can I know who's over there? So may I know who's around? Didn't see anything anybody. Oh, share privately. So how can I make it share privately? Okay, never mind. Okay, so we are going to talk about charge carriers today, basically. Yeah, what are charge carriers in a semiconductor? Just as a revision. And then how to classify the charge carriers in a semiconductor. And how to calculate the charge carrier concentration in a semiconductor. So basically we are about charge carriers today. Okay, so what are the charge carrier in a semiconductor? So basically, can anybody say anything about what are the charge carriers in a semiconductor? I didn't see anyone. As you might as well know that, yeah, charge carriers in semiconductor are electrons and holes. Basically, what you have learned before is only about electrons in metals, but now we are going to add another charge carriers, yeah, because in semiconductor we do have holes that acts as the conducting agent. Okay, but basically, what are holes? If you can recall our conduction band and our valence band, basically all at 0 degrees, at 0 K, most of our electrons are in the valence band. Yeah, when there is an increase in temperature, then there is a possibility for our electrons to jump into the conduction band. But what's left behind are vacancy at the electron side. Yeah? Since our semiconductor is neutral, then what's left behind is positively charged. So you see this is an unbonded site, yeah, where there is a vacancy of electrons here. So looking at this, vacancy at the bonding site, so we can define our holes as the positively charged vacancy at the valence electron site. So you see here, the key word is, if you look here, just highlight in the highlighter, it's at the valence electron site, at the valence of the outermost electron, positively charged. Okay, so okay, so that's basically what holes are, which I guess most of you already knew. But how does electron transport in conduction band? So we know that electron moves in the conduction band. But the thing is, how about hole transport? We know that electron transport is through random thermal motion. But how about our hole transport? So let's look at this animation so that you can have in your mind, how does the hole movement in the valence band? You must remember that hole moves in the valence band and electron moves in the conduction band. So look at here. So let's say, there's one electron that jump out from its bonding site, and another electron will take part will take the place of the one that has been that's jumped into the conduction band. So you see that electron moves this way, but the hole moves the other way around. So let's look at it again. The next one. Okay, so it jumps. So what can you conclude about the hole transport? So it's in the opposite direction to the electron transport. So electron to run random thermal motion and hole is in the opposite direction to the random thermal electron transport. So that's basically what our charge carriers are, electrons and holes, and how do they move? What are their movement? Because this movement, as you know, is the one that allows for conduction to occur, electrical conduction to occur. Okay, so we have talked about what are the charge carriers in the semiconductor. Next, we are going to go to how to classify the charge carriers, because it's very important for us to classify it, because especially at high temperature, there is a tendency of an intrinsic semiconductor, of an extrinsic semiconductor turning into an intrinsic. Because, as you know, that our devices, it's not advisable for us to put it under the hot sun, isn't it? What are the places where the temperature is high? So, in order to explain this, we need to classify the charge carriers in the semiconductor. Okay, so you know that the charge carriers are electrons and also holes, and also from our previous JIF conference, from our our charge carrier being electron and also holes. And of course, we knew that there's two types of semiconductor, intrinsic and extrinsic. As for the extrinsic semiconductor, we know that there's N and P type. So, if we look at electron, in an intrinsic semiconductor, the electron comes from the holes of the semiconductor. So, it's an intrinsic carrier. And holes, it's from the holes semiconductor, so it's the intrinsic carrier also. And as for the extrinsic semiconductor, if we look at the electron, of course you know that is the majority carrier. So majority carrier, it's for electron is also an intrinsic carrier. But the thing is, because of our dopant, we are introducing electron into our semiconductor. So the electron that comes from doping are extrinsic carriers. Okay? So, in an extrinsic semiconductor, we have two sources of electron. One from the whole semiconductor itself, and another one from the doping elements. Okay, if you want to, since I'm at home, if you want to ask questions, yeah, please chat to everyone and not privately. Okay? Because I don't seem to get any response from anyone in the chat group. So please, yeah, if you would like to ask any question, please send it to everyone so that we can know what you are asking. Because if you send it privately, I won't see it because I'm at home. Because I'm not at PPJJ. Okay, so let's continue. So, if the host is the minority carrier, and of course, our doping is only, let's say we doped donor dopant, then we only have the extrinsic carriers, but not the extrinsic carriers for host, unless we doped it with both acceptor and also a donor. But in the case of we only are doping the donor, then only we have electron as extrinsic carriers. Now, for the p-type, of course, yeah, we know the electron is going to become the minority carrier and the electron are the intrinsic carrier. And for the majority carrier host, of course, is similar as that in the electron in the p-type. We have both, yeah, the host from the host semiconductor and also the host from the from our acceptor elements. Okay, so that's we are talking about the sources, yeah, from the origin of the charge carriers, yeah, in an intrinsic semiconductor and also an extrinsic semiconductor, because all these extrinsic carriers comes through a doping. Okay, now the crux of the matter is, this is what it is all about, yeah. How the charge carriers change with temperature. So this is the ratio of the charge, and this one is the x-axis is the temperature in Kelvin. Where if you look at 0 Kelvin, most of the dopant, the extrinsic carriers are, let's say this is for N, silicon. Yeah, most of the electrons are at the acceptor level. At low T, you can see that some of the electron from the acceptor level has jumped into the conduction band, whereas only negligible number of electrons from the valence band to jump into the conduction band, because the band gap is high, isn't it? Then not enough temperature for it to jump, because it needs energy to jump the band gap. So let's just write down here. So this is, change the color. Okay, this is the E gap, yeah? This is the E. So, in order to jump the E gap, it needs to have the appropriate amount of energy for jumping from here to here. But at low temperature, the thermal energy that's being given hardly is much less than the E gap. So only a few that can jump, make the jump. So you can see here that at low T, some of it, only a little bit. But when we look at the moderate, we can see that, more electrons. Of course, the one in the acceptor level has jumped into the conduction band, and also some of the electron in the valence band have enough energy to surmount, to jump through the E gap. So you can see that after a certain time, at a higher temperature, most of the electron has already, that have sufficient energy, has already jumped up into the conduction band. So you can see that, initially that's more and more as the temperature increases until around about 150, you can see that it's already flattened out. But the thing is, at a much higher temperature, because you can see that here, there's still available electron in the acceptor level. But at a much, much higher temperature, we can see that electrons from the valence band have enough energy, to jump through the E gap. So, at around 400 K for silicon, we can see that, there is a substantial amount of the intrinsic carriers they are able to jump to the conduction band. So at high temperature, it's the extrinsic carriers that dominate. So from here you can see that, at high temperature, our extrinsic semiconductor now is no longer extrinsic, because whether it's extrinsic or intrinsic depends on the amount of the charge carriers. But since the host atoms, the host charge carriers dominate, then it means that it's no longer being extrinsic, and now it's acting like an intrinsic semiconductor. So, is there any question? Okay, you can write. Is there any question? Is there any question? Please choose whether you would like to have everyone or I can see that there's Ifa, there's Muhammad Khairi, and there's Raja Sharif. But the thing is, Ifa, if you would like to ask questions, please, at the stand tool, change it to everyone. Also for Khairi and also Sharif. Yeah, because I'm at home. Yeah, because I cannot see, if you have any question. Okay, Khairi, do you have any question? As for this particular junction. Because the thing is, extrinsic semiconductor can become an intrinsic semiconductor at high temperature. So this is how you are going to explain it. So I hope all of you get it, So that's why we need to know what are the sources of the charge carrier, so that we are be able to explain this phenomena. And because of that, intrinsic carrier is very difficult to control. Because if you know that for intrinsic charge carrier, it's very difficult to control. But if you see here, in extrinsic carriers, you are able to control it by having a certain kind of temperature. At a certain temperature, you know that there will be a certain amount. you know there will be a certain amount. But once, at high temperature, you are not be able to control the amount of the charge carriers, the total charge carrier. So that's why our devices, most of our handphones and our computers, all have a certain range of temperature that they are going to work best. Okay. Okay, I hope you, since nobody asked anything, let's move to the next one. Okay, let's go to how to calculate the charge carrier's concentration in semiconductors. So now we are more on calculating it. So what are the equations that we are going to use? Okay. Most of the terms that we are going to use are the carrier concentration per unit volume. So, which is either N or P, depends, N is for electron, P is for holes. There's a sub-zero there, means it's at equilibrium, where it's equal to the integration of the density of states in the energy range E, multiplied by the probability of occupancy either by electrons or by holes, and we integrate it across E. And the density of states is the number of energy states per unit volume. Of course, the word density should have come into your mind. Say, it must be something per unit volume, isn't it? Okay, or in short, you can have it in the form of density of state. The symbol is Ne, and the probability of occupancy is F as a function of E. Okay, now let's look at how it actually is in terms of energy band diagram. So let's say we have our density of state as in the x-axis, and that's our conduction band H, E sub C. We can have it, we know that the energy of the electron increases as we go up higher along the xy axis. And we can write, this curve represent the conduction band H. And we can, quantify this in the form of this expression, energy density. We can, collapse, all the density of electrons per unit volume in the conduction band by using this equation, the effective density of states, but this one is for the conduction band, so N sub C, where N star sub N is the effective mass of electron, because the thing is our electrons are in a crystal. So we need to make some correction to the mass, since it is the effective mass and not the mass of the free electron. Shortly I will show you what is the value of it. And of course H is the Planck constant and square root of E wherever your energy level is and your EC. So you just use this equation to get the density of states at particular E, at a region in between. Say get our E somewhere around here, so we can find what are the density of states in this particular region. Okay, so you can find what are the density of states in this per unit volume. Alright, so by using that one. Okay, we can use that one, that equation. Alright. and the number of energy states increases, yeah, as the number of, you can see that it's curving this way, yeah, curve this way, so the number of energy state increases as you go up along the y-axis. Okay. Okay, for the electron valence, yeah, electron hole increases as we go towards y negative, and that's for the holes here, where you use n sub v. So for holes is n sub v, for electron is n sub c, because we know that the movement of electron is in the conduction band, whereas the movement of holes in the valence band. Okay, n sub v and n sub c. So similar to that one, so you can see that as it's curved downwards, yeah, the number of energy state increases as we go along towards the y negative. But if you look here, yeah, that's one, energy state increases, But what about the energy states between the EC and EV? You don't see any energy states here. And of course, if you look here, when there is no energy state, means your semiconductor is an intrinsic semiconductor. Because we know that, as you saw just now, that when it is an extrinsic, you are going to have that acceptor or the donor level, isn't it, in the energy state. But when there is no energy state, then automatically you know that it's an intrinsic semiconductor. Okay, so the density of states, yeah, we use this equation. It looks very daunting, isn't it? But not to worry, because in exam, yeah, this value is going to be given to you, n sub c, E of E, yeah, the effective density of state is going to be given to you. But nevertheless, let's have a go at it and see how it's going to be calculated. Okay, let's see. Yeah, we would like to determine the silicon total energy density between EC and EC plus KT at 300K. Sorry about the Malay here. But anyway. Okay, so how are we going to find the silicon total energy density? So it's just that between EC and okay, so we would like to know what are the total energy density EC plus KT. EC plus KT. Okay, so we would like to know. Okay, we would like to know what is the energy density. So where this one is EC plus KT. Alright, so we would like to know what are the energy density in here. Okay. So to go about doing it, so of course our equation just now, so where our E now is EC plus KT. So that one. You can see here, so this is 4, and then 4, 4, 5, and your M star, your effective mass of electrons,